MATH5130. Before we get into running logistic regression models and reporting the results, we need to pump the brakes a little bit and study something. Let me introduce at least to you something that we use to determine the model effectiveness. And so the purpose of this video is I'm going to introduce to you sensitivity and specificity. We're going to talk about true negatives, true positives, and all that stuff. And we're going to talk about percentage of accurately classified cases and error rates. So let me tell you what's going on here. So we have this relationship that we want to examine. Our dependent variables, categorical, dichotomous, and we have this set of predictors we're going to use. Once we create our model, we can follow up with something called a confusion matrix. And a confusion matrix gives me a 2x2 matrix of the observed values, whether it happened or it didn't happen. So again, let's bounce it off the fall status. They did not fall versus they did fall. And then we have a way of using our model to determine a prediction status. So let's say our model can predict the patient not to fall, or they can predict the patient to fall. Again, based on this set of predictors, react and age and cane and all that stuff, whatever it may be, we get these outputs of what we actually observe from our data and what our model actually predicts. Now, there's going to be one of four classifications. We're either going to get it right, in which case we did not observe a fall, and our model predicted no fall, or we get into something called a true positive. This is called a true negative. True positive, where our model predicted the person to fall and they actually did fall. These are the error components. Right here we have a false positive because the patient did not fall, but our model predicted them to fall. And here we predicted the person not to fall, but they actually did, so that's also an error, and it's called a false negative. I think about COVID. Again, I just got done with COVID, or at least I hope I'm done with it. And when I took a COVID test, I always thought about the possible outcomes. For example, my COVID test could result, it was either going to show a positive or a negative. And the truth of the matter is, I either had COVID or I didn't. So if I really didn't have COVID and my COVID test result was negative, then that's a true negative. That's, 2 thumbs up. That's good. This cell down here represents if I did have COVID and the test result showed that I had COVID, positive result, then that's a true positive. Knowing, what I know about statistics, when I take one of those tests, I'm always thinking about these two boxes right here. I'm kind of the negative thinker in a way. Well, what if I have COVID and the test result is negative? That, what happens there? Well, I'm out here running around, positive of COVID, but I don't think I have it, so I'm, contagious and potentially spreading it to other people. This box here, I really don't have COVID, but I get a positive result, so I'm quarantining when I really don't even need to quarantine. So, we hope for these true results, the true negative or true positive. We hope for the test result to represent what we have in terms of COVID, and we hope that we don't get one of these false results. But we never know. It's just all based on probability. We'll expand that just a little bit. Let me see if I can get that just a little clearer. Expand that a little bit into something we call sensitivity, specificity, and percentage of accurately classified cases. So sensitivity is just the ability to correctly identify a positive case. Specificity is the ability to correctly identify a negative case. Percentage of accurately classified cases, which we typically abbreviate to be PAC, is exactly what we say it is. What percentage of cases were accurately classified. Now, to calculate the sensitivity, I always calculate it first, because if I set my table up correctly where I have no's and yeses followed by no's and yeses. A lot of times our tables will be given as like yes, no, and no, yes, or yes, no, and yes, no, or no, yes. You know, if I can make the table into no, yes, and no, yes, then these formulas I'm giving you follow perfectly. So I always do that, and I just know that sensitivity is the one I'm going to look at first because E comes before P. And I have just tunnel vision, and sensitivity is going to be on this last line. So again, sensitivity, the ability to correctly identify positive cases. I'm looking at positive cases. I'm looking at the true positives divided by the total of, in this last column, TP plus FN. Specificity focuses on the first column. It's the true negatives divided by the true negatives plus the false positives. So I don't even remember in terms of true negatives and false positives. I just remember sensitivity goes to the last column, bottom number divided by this number plus this number. Specificity goes to the first column, this number divided by this number plus this number. That's the way I remember it. Percentage of accurately classified cases will be the sum of the two that were accurately classified, the no-nos and the yes-yes, the true positives and true negatives, divided by all of the cell counts. So in other words, it's the true negatives plus the true positives divided by our total sample size. The error rate is just the sum of the errors, the false positive plus the false negatives, divided by the total sample size, or you can find the error rate by just taking 1 minus the percentage of accurately classified cases. Should make sense that if something's accurately classified, if it's not accurately classified, then it's an error. So let's look at an example. So let's say that we have a situation where the person either has the disease or they don't, and their blood test is either positive or negative. Well, the first thing that I would do is I would realize that this is not in the form I want. I want no yes and no yes. Absence of, has it. Absence of, has it. So I would restructure the table to be in that form, again, because this can be tricky, but if you always put your confusion matrix in a form of, again, no yes and no yes, you can use the formulas quite easily to calculate PAC, sensitivity, and specificity. So I do that. 245 is true negatives. It's in the no-no box. 134 is in the true positives. 134 and 11 and 7 are where they should be. So sensitivity, what do? I have tunnel vision on the last column. It's 134 plus 11, which is 145. So my sensitivity is 0.924. So 92.4% of those who were observed to have the disease were actually positively classified. Specificity looks at the first column, 245 divided by 245 plus 7, which is 252. The specificity looks at the accurately classified cases of the negatives. So 245 out of 252, or 0.972, were accurately classified in terms of correctly identifying negative cases. The percentage of accurately classified cases would be these two values, which is 379 divided by the total, which is 397. So a very impressive 95.5% of our cases were accurately classified. The error rate, in other words, the percentage of those that weren't accurately classified, would be 7 plus 11, which is 18, divided by 397. So this is a table, a confusion matrix that we're going to see a lot in logistic regression. And so I thought it kind of deserved its own video in terms of describing these calculations to you. All right.